Hi, my name is Remy Arnold, and welcome to my presentation for the CIS 1942 internship. The main topics of this presentation include an introduction, where I'll be taking you to Lausanne, Switzerland. We'll be looking across at a large mountain range and imagining that is all data. We'll be talking about the main topic of the presentation of understanding what big data is, its origin, and what it can do. Big data architecture, big data terminology, the skills and knowledge utilized and learned over the course of the semester, both at the community college where my internship was held and at another organization and big data project, and then a conclusion for the presentation. So we're off. We're in Switzerland. We're sitting in our favorite hotel, having our favorite beverage and looking at this gigantic mountain range and imagining that it's made of data. How did that happen? Well, over time, as you can see through the global information storage capacity, things have really changed. It used to be that information was mostly stored in analog form, in textbooks and audio, but as more and more information has been created, more and more data has been created, it's been stored digitally. And as you can see, by the year 2002, officially, we had the beginning of the digital age. And a huge amount of information is being created every single day. And we have to figure out what we're going to do with it. And there comes the origin of big data. Think about the gas, grocery, and online purchases you make, your social media posts and likes, and how telecommunication company cell towers are used to track your constant movements based upon the location of your phone and other mobile devices you carry around on a daily basis. Companies are building their entire businesses around the collection, analysis, and sale of data about us. And no one really knows what all that data and the information drawn from it is truly worth. Data isn't a physical asset like machinery or cash, and there aren't any official guidelines for assessing its value. Gartner claims that companies have better accounting methods for their office furniture than their informational assets. One problem with data being an intangible asset is you can't manage what you can't measure. As more companies collect and sell information and use big data analytic tools to find ways to generate revenue, the lack of standards for valuing data leaves a widening gap in our understanding of the modern business world. Corporate holdings of data and other intangible assets such as patents, trademarks, and copyrights could be worth more than $8 trillion according to the U.S. Federal Reserve Bank. Thus, data and the information derived from it is increasingly becoming a more important part of our global economy and is growing at an accelerating rate. Yet the value of such assets to technology-driven companies like Apple, Google, and Samsung does not appear as a line item within their corporate financial statements. The concept of big data is still evolving. It continues to be a driving force for business model disruption, digital transformation, and the growth of data science, machine learning, artificial intelligence, and the eventual global web coined the Internet of Things. The exponential explosion in the amount of data humankind generates is mainly due to the rising usage of computers, the Internet, and technology capable of capturing data from the world we live in and converting it into a digital form. Data is also generated when our home appliances and mobile devices communicate with each other and with in-home servers. Industrial equipment is being produced with sensors that collect and share data. Self-driving cars are mapping the roadways of entire countries. Well, what can big data do? Today, big data projects are working towards things like making our everyday lives easier and more convenient, such as asking Alexa to add an item to our grocery list, or give us the latest weather report. And other important life-saving answers it is providing include curing disease and preventing cancer with data-driven medicine involving analyzing an enormous amount of patient medical record notes, X-rays, CT scans, and MRI images for patterns which can help spot disease early on and help develop new medicines to treat those diseases. How does big data work? Big data relies on the principle that the more known about anything or any situation, the more reliable new insights and predictions can be made about what will happen in the future by comparing more data points, relationships will begin to emerge that were previously unknown, and these relationships will enable decision makers to be better informed. This is the most commonly accomplished by designing and constructing software models based upon collected data, running the data through simulation models, refining the value of data points, and measuring how each adjustment impacts the outcomes. Simulation is a computer automated process capable of executing millions of simulations, capturing the data, then analyzing all the possible variables until a pattern is discovered or an insight is made that helps solve a problem. Data is increasingly originating in an unstructured form, so it cannot easily be placed into a relational database with structured tables made of rows and columns. Much of this non-relational data is in the form of pictures and video streams, including photographs uploaded to Facebook, personal tweets on Twitter, emails, instant messenger texts, and recorded phone calls. To make sense of unstructured data, big data is required, as well as utilizing advanced analytics such as machine learning and artificial intelligence. Teaching computers to identify what data represents through image recognition and natural language processing enables them to spot patterns millions of times faster and more consistently than humans, because our minds operate at the speed of our physiology, while machines operate at the speed of electrons. And here we have a picture of big data architecture with some new names. We have NoSQL, and we have non-relational database structures. We have online application processing engines, reporting. We have the extraction, transformation, and loading of data coming from a multitude of business databases and web logs, going through that type of transformational process and into what's called Hadoop and HDFS, along with the supporting applications such as Impala and Pig. Well, now on to just a taste of big data terminology so we can get into the meat of definitions and an understanding of big data. Avro, it's a serialization system for storing and transmitting data over a network. Apache Avro supports rich data structures, a compact binary encoding and container file for sequences of Avro data. Bindings are available in different computer languages to allow it to work with Java, C, and C++, as well as Python and Ruby. Big data. Data sets in which the input-output velocity, variety of data structure, and volume exceed the capabilities of systems which were designed for smaller data sets to capture, manage, and process the data within a tolerable elapsed time. Big data sizes are expanding, currently ranging from terabytes to many petabytes in a single data set. Cluster. A set of computers or racks of computers that contain an HDFS file system that run MapReduce and other processes on that data. Flume. A distributed, reliable, and available system for efficiently collecting, aggregating, and moving large amounts of text or streaming data from many different resources to a centralized data store. Hadoop. A free, open source software framework that supports data-intensive distributed applications. The core components of Apache Hadoop are HDFS and the MapReduce and Yarn processing frameworks. The term is also used for an ecosystem of projects related to Hadoop, under the umbrella of infrastructure for distributed computing on large-scale data processing. Hadoop Distributed File System, or HDFS, a user space file system designed for storing large files with streaming data access patterns running on clusters of industry-standard machines. HDFS defines three components: a name node, a data node, and a journal node. Hive, an Apache data warehouse system for Hadoop that facilitates the summarization and the analysis of large datasets stored in HDFS using SQL-like languages called HiveQL. The HiveQL, the name of the SQL dialect used by the Hive component. It uses a syntax that is similar to the standard SQL to execute MapReduce jobs on HDFS. Impala. The official name is Apache Impala, which stands for incubating. It's a service that enables real-time querying of data stored in HDFS or HBase. It supports the same metadata and drivers for databases as Apache Hive and a query language based on the Hive standard query language. MapReduce, a distributed processing framework for processing and generating large data sets and an implementation that runs on large clusters for industry standard machines. Maven, a software project management tool based on the concept of project object model. Apache Maven can manage a project's build, reporting, and documentation. Parquet, an open source, column-oriented binary file format for Hadoop that supports very efficient compression and encoding schemes. Parquet allows compression schemes to be specified on a per-column level. So in other words, in the last diagram that we looked at for big data architecture, we pulled information in from relational databases, such as Oracle database or MySQL, converted it into Parquet format and in a columnar format for better analysis of the data. Pig, data flow language and parallel execution framework built on top of MapReduce. Internally, a compiler translates Apache Pig statements into a directed acyclic graph of MapReduce jobs, which are submitted to Hadoop for execution. Spark, Apache Spark is a general framework for distributed computing that offers high performance for both batch and interactive processing. It has APIs, or application programmer interfaces, for Java, Python, and Scala, and consists of Spark Core and several related other projects, including Spark SQL, Spark Streaming, MLlib, and GraphX. By the way, Cloudera supports Spark Core, Spark SQL, including data frames, Spark Streaming, and an MLlib. Scoop. Scoop is a tool for efficiently transferring bulk data between Hadoop and external structured data stores such as relational databases. YARN is an acronym for Yet Another Resource Negotiator. It's a general architecture for running distributed applications. YARN specifies many components, including a resource manager, an application manager, a node manager, and a job history manager, which keeps track of completed applications. Zookeeper, a centralized service for maintaining configuration information, naming, and providing distributed synchronization and group services. In a Cloudera cluster, Zookeeper coordinates the activities of high availability services, including the HDFS, as well as Hive, YARN, and other applications. So throughout this semester, within the community college internship, as well as working with an outside organization, I was able to build programs in C, C++, and using Java 8, extract and transform relational and non-relational data so it could be input into Cloudera. I'm learning the Scala programming language, which is used with Spark. I'm learning the overall big architecture that I showed you in the prior diagram, which is very complex and has many moving parts. I am currently working in the Android development environment for mobile devices using the Java 8 programming language and making existing programs Android compatible, as well as writing new Java programs that are automatically compatible with Android, and writing information to system logs concerning applications and how they are used by the end user. In conclusion, I have found many points that are pertinent to big data. The systems are incredibly complex and expensive to design, build, and operate. Yet the demand for big data information technology talent is rising and will continue to rise. That is because companies and governments want to predict the future to make better informed decisions. And that's due to the insights from emerging technologies that will continue to shape our world. So it's kind of like a circular function where we can predict the future, then we can modify it, and then the future modifies our decisions. Thank you so much for listening to my presentation.